Everyone has used image filters before, for example, to blur an image. But what exactly happens in terms of math? To give a small teaser, it looks like this. In 5 minutes you will understand what happens here and you will see other examples. Spoiler! We describe our images as interfering waves. But let's build this up step by step. We start with the so-called K-space. This is an array, in this case with 19 times 19 pixel and a center in the middle. The arrow at the top defines the y direction. Let's also introduce the so-called real space. How are they related? Best, we just place one peak into the K-space and see what happens. We saw a peak 1 pixel left from the center yields 1 vertical oscillation in real space. A peak 3 pixel away from the center yields 3 vertical oscillations in real space. Now some further examples to get a feeling for the relation. One thing to note here. Our end goal is to produce an image in the real space array. Images have only positive values, so we cast all negative values to 0. What we know by now? We can insert peaks in K-space. Their positions correspond to frequencies in the real space image, respectively in x and y direction. The height of the peaks corresponds to the amplitudes of the real space oscillations. But we know that oscillations also have phases, so we have to find a way to visualize these. To accomplish this, I had the idea of phase flowers. We can grow again an amplitude, and on its top we grow a flower. From 0 to pi half, to pi, to 3 half pi, and to 2 pi. In my opinion, this is a good analogy because the life cycle of a flower is also a periodic process, just as the phase change. Now we can see what happens to the real space image when we change the phase. Beneath the real space image, you can see the original without the phase change, just as a reference. To get used to it, here are some more examples. Instead of one peak, let's try the same with more peaks and vary their amplitudes and phases. At this point, it might be obvious that we can describe images with these K-space peaks. Let's try to build up an image. First, we insert low frequencies close to the middle. And after a while, you can see kind of a circular object. When we insert even more frequencies, the object gets clearer and clearer. The highest frequencies also define the edges of the object. In this case, I did not show the faces. They would actually look like this. From now on, I won't show the faces anymore, because it looks quite too overwhelming. But it's important to keep in mind that they still exist. Cool! Now we have all the tools to go on to the heart of image processing. First, we take an input image and make a Fourier transform to create the K-space. If you want to know how this is done, check out the Fourier series videos from 3 Blue 1 Brown, who also inspired me to make this video. For now, we just have to know that the Fourier transform of an image with 601 times 601 pixel produces an 601 times 601 pixel K-space array. But the displayed K-space has only 9 times 9 pixel. Yeah, but it's zoomed close to the middle just for visual reasons. This is also denoted by the plus sign at the bottom. When we modulate now one peak, for example one at the right side, we see that the corresponding frequency is also enhanced in the image. This can be useful when one has a picture with a periodic artifact. It might be that one took a picture at night of a fantastic galaxy, but some defect in the lens produced a periodic oscillation in the image. You might have guessed what to do. Look into the K-space, find the annoying frequency and decrease it. The result looks impressive. Finally, let's go on with image blurring. Also in this case, you don't see the whole K-space. Instead, it is downsampled. Only every 26th pixel is visible. All the others are hidden. Downsampling is denoted with an O at the bottom. We want to blur the image. That means removing high frequencies. So let's draw a filter function and see what happens. Every amplitude is multiplied by the filter function. The filter function slowly becomes a Gaussian shape, so all high frequencies are muted, where the low frequencies are nearly untouched. That's why this filter is called low-pass filter. When there's a low-pass filter, there must be a high-pass filter as well. And intuitively, the high-pass filter is a reversed Gaussian filter. Now we mute all the low frequencies, and what remains are the edges of the image. That's it. Thanks for watching and don't forget to subscribe.